So good morning to everyone. I will talk about an optical SDN controller. It's an optical SDN controller based on the TeraFlow architecture. Is a work carried on within the framework of an European project called FlexScale. I would like also to thank my colleague Andrea Sgambelluri. So the objective is to design and implement an SDN controller that controls an optical network. So we are targeting, let's say, a next generation optical network. So an optical network designed to accept the traffic growth. So offering space dimension through parallel fibers and also offering wideband transmission, so multiband like an S plus C plus L system. So I would like to talk about some definition to avoid any misunderstanding. Now we will call band like S or C or L band, we will call them window. So S window, C window. And for band, we will consider a wide portion of spectrum that can include more channels and can be a full window like the S band or a portion of this window. So this optical network will support wavelength switching or band and also band switching. So basically, based according to an optical service request, the optical SDN controller performs two main tasks: the resource allocation and then the device configuration, so the data plane configuration based on NetConf protocol and Young data modeling. So for devices now we are considering transponders and also the optical node. So few words about the band switching. For band switching, we are considering this kind of scenario. So we can set up within a network, a band circuit. So as I told you, a circuit with a wide spectrum, and inside this circuit we can accommodate some channels. This optical band can have a dynamic reconfiguration. So, for example, we can enlarge its spectrum in order to accommodate a larger number of channels, like in this example. So we can reconfigure the bandwidth of this optical band in order to set up new channels or tear down already established channels. Okay. Regarding the optical SDN controller, so it's based on the TeraFlow architecture, so which is the impact on the TeraFlow architecture. So the main impact is the inclusion of a new component, which is the optical component. But there is an impact also on other components, like the northbound interface, the service component, and the southbound interface. So let's start with the optical component, which is, I would say, which is the core of this optical SDN controller. Here you can see an high-level architecture. So let's start from the left side. You can see the reprovisioning manager. This module inside the optical component triggers resource allocation. And we have three use cases for resource allocation. So the first use case is the provisioning of an optical service. The second use case is the re-optimization of some optical services, so we can reallocate the resources for network optimization, or we can trigger resource allocation for recovery purposes. So we can reallocate the resources after a failure, after a soft failure, which mean a physical layer degradation. So based on these three use cases, the provisioning manager triggers the resource allocation. So triggers the what is called in more or less in the middle of the figure the flex scale routing and spectrum assignment engine. So this engine generalizes the concept of routing and spectrum assignment. Why I talk about generalization? Because based on the characteristic of the optical network we are talking about. So in practice, so the engine has to allocate to an optical service, for sure, a route within the network. It also has to perform quality of transmission estimation. This quality of transmission estimation depends for sure on the route, but depends also on the multiband scenario we are considering. This is due to physical layer effects like stimulated Raman scattering, which is particularly relevant in a wide band transmission scenario. According to the quality of transmission estimation that can return a figure of merit like the generalized signal-to-noise ratio, at this point we are able to decide which is the supported modulation format. Or in the case we are considering an open config data model, we are able to select a proper operational mode. So the operational mode, it's a specific combination of modulation format, symbol rate, and forward error correction, which finally drives a given line rate. So based on this estimation, we have the operational mode. But this operational mode, so with that specific line rate, is able to support the requested line rate. If so, okay, we have to establish one channel. But if the line rate is not supported, maybe we need more channels. So this engine is able also to select the proper number of channels to meet the rate requirements of the service. The operational mode and this number of channels will also drive the bandwidth requirement of this service. So the portion of spectrum that we need to allocate. So in practice, the spectrum assignment. Moreover, we have to, the engine will also account for the several parallel fibers deployed within the network, and will account also for band switching, so for available band circuits or reconfigurable band circuits. This engine exploits a set of databases, a traffic engineering database, a label switch path database, and a physical layer database to perform quality of transmission estimation. So let's go to see the workflow. We have an optical service request coming from a northbound interface that might be connected to an orchestrator, for example. This request from the northbound interface is propagated to the service component of TeraFlow. At this point, there is a module inside the service component, which is the service handler, that sets some parameters, which actually are the source and the destination of this optical service, and the specifications. For specifications, we can consider exactly the line rate requested for this service. We are also, it's not shown here in this slide, but we are also encompassing some optional information. We are considering this optional information for use cases of re-optimization and recovery. But now let's focus just on provisioning. So we are at the service component that specifies the source, the destination, and the specifications of this optical service. And then the service component triggers the new optical component. The optical component finally performs the flex, the routing and the spectrum assignment. Once the routing and spectrum assignment is run, the optical component goes to the southbound interface. So the southbound interface is the component of the controller that actually performs the configuration of the data plane, and we are considering an SBI based on an NetConf plugin. So what is important to say is that the optical component, after running the flex routing and spectrum assignment engine, this component has also to translate the output of this algorithm into the devices to be configured, also together with their configuration parameter values. So these, which are expressed in Young-based parameters, Young-based values that are propagated actually to the southbound interface. So at this point, we are considering for Young model, we are considering OpenConfig. For example, for the transceiver, you can see the list of logical channels with configuration and state parameters. I would like also to highlight the component, the list of components with a central frequency, a target output power, the operational mode to be configured in the transceiver, and some state parameters. So here I can see that, well, those are related to the mainly to the coherent receiver. I can see that now is missed some parameters like bit error rate or electrical signal to noise ratio. Here you can see an example of the content of an edit config message going to set to this transceiver this central frequency, this output power, and the operational mode with identifier 3. For the node is still based on OpenConfig, but it's an enhanced model, for example, to model the optical bands. So here you can see the augmentation on the left side. We have a list of optical bands with the configuration parameters, so we can define the lower and the upper frequency. We can also define the associated fiber identifier. And for this, I would like to thank a colleague, Michael and Enrico, in the framework of the flex scale projects. More details of this model can be found in this public deliverable. a recap on which is the impact on the TeraFlow architecture. The impact, as I already mentioned, is first of all, on the northbound interface, which is extended to accept a request for optical service. It's another impact is on the service component, which is extended to trigger the new optical component. So another impact is the introduction of the optical component in the architecture. And finally, there is an impact on the southbound interface, which is extended to control space division multiplexing and multi-band wideband transmission optical networks supporting band switching, which is the status of this implementation. The northbound interface, it's in progress. We are considering a REST interface. The service component is in progress. There is a first implementation of the optical component handling parallel fibers and multiband, and also optical band switching. And there is also a first implementation of the southbound interface, considering the previously reported young models and netconf. Basically, we are targeting we are still targeting the integration of the optical component within the TeraFlow architecture, and these other components are in progress. We are working on it within this FlexScale project. So thanks for your attention.
Thanks a lot, Nicola. It was a very interesting talk. Is there any question on the room or live?